sweeping convection cells of plasma, you're going to get an interface of plasma between those two
Yeah.
zones.
Sorry, can I interrupt you just for a moment to
You
say that
very well
I
can.
think we're live now? Um,
Gosh, great.
and if we could start over.
We can totally start over. I'm so sorry. Let me just text my wife.
I'm so sorry.
Yeah, I
Oh my goodness.
think it's fixed now. And difficulties. Sorry, world. I'm just texting my spouse where I am. All right, let's. Okay.
Let me
All right,
just
Kelly, where would you like to begin?
uh from the beginning
From the
because I'm
beginning. I love
so
it.
sorry. All right, we are live.
Yay.
Fantastic. Oh, we are live. I am so sorry, world. Okay. Well, let me start at the beginning and apologize a billion times to our dear guest, Dr. Rebecca Robinson. So it turns out there's an extra button you have to press when you want to go live on YouTube. Who could have figured that
I did
that was
not know
the way
that.
that things work? I am so sorry. So I'm going to do our introduction once again so that everybody gets to hear how amazing Rebecca Robinson is. So my name is Kelly Blumenthal. I am the director of the Office for Astronomy Outreach at the International Astronomical Union. We are based at the National Astronomical Observatory of Japan in Tokyo, which is where I am right now. And we are doing this webinar series, The Women of Solar Physics, because not only are we celebrating International Women's Day, at least still in some parts of the world, but we're also celebrating the solar maximum in 2025. So that means that the sun is particularly active, and we'll be able to see a lot of really interesting things like aurora will be really prominent. The solar corona will be really exciting. And that means that solar weather will be really interesting, or space weather will be really interesting as well. So our first speaker is Dr. Rebecca Robinson. And I am going to read her bio because she's exceptionally interesting, and I want to get everything right. Here we go. So Rebecca is Michigan born and a Norwegian transplant, and she now is returning to the United States to work with NASA's multi-slit solar explorer project, which is called MUSE. She's a curious and driven researcher who has worked on projects worldwide, from drilling ice cores on Icelandic glaciers to analyzing solar MHD simulations from her couch in Norway. She received her bachelor's in physics and astrophysics from Michigan State University, a master's in geophysics from the University of Iceland, and a PhD in theoretical astrophysics from the University of Oslo in Norway. In terms of outreach, she's been visible on nearly every platform imaginable, from schools, museums, universities, national parks, cruise ships, virtual classrooms, and social media. Her favorite outreach projects so far have been serving as the resident astrophysicist for the Badlands National Park and sailing along the Norwegian coast with a cruise ship as a solar and aurora scientist. In her spare time, she enjoys bouldering, singing, foraging in the forest, collecting cool rocks, hiking, traveling, stargazing, road tripping, making pancakes, and putting together puzzles with her wife. She is a born communicator with a trained science background who enjoys making hard science accessible to everyone. Thank you, Rebecca. Thank you so much for restarting your talk so that everyone can experience the beginning of your talk. And I'm going to give it away to you finally, hopefully for the last time.
No worries. We love giving talks multiple times. That's what we do. Hi, world. Hi, everybody. I'm so inspired and honored to be here together with you on this most auspicious occasion. And I just want to note really quickly that I'm headquartered at the SETI Institute in Mountain View, California. And I'm in one of our conference rooms. This conference room is dedicated to this lady right here. This is Hedy Lamarr. She is credited with developing the technology that eventually led to Wi-Fi. So we have her to thank for our connectivity and our global ability to communicate with one another today. So, like Kelly said, I am Becca. I am currently working as the outreach lead for NASA's MUSE mission, headquartered at SETI. And I I'm so excited to be able to be here and tell you about one of my very favorite things, which is the sun. Now, we have such interesting relationships with the sun, every single one of us, whether or not we think about it. We have daily relationships with the sun, we have seasonal relationships with the sun. The sun dictates what we do here on this planet. And there's so many ways of knowing and understanding those relationships. So, I'm going to tell you about a couple of my favorite ways of knowing about the sun, especially in my professional work. And some of those ways are using telescopes and satellites, and some of those ways are using computer simulations. And we're going to talk about both of those things today. But first, even though Kelly gave a really nice comprehensive bio of me, I'm going to go over this just briefly one more time. I did grow up in Michigan, so shout out to any Michiganders out there. I did my bachelor's degrees in physics and astrophysics home at Michigan State University, so go green. And then eventually I moved very far away to Iceland, where I got my master's degree in geophysics. So this is why you see this very strange picture of a solar physicist drilling an ice core on Iceland. These ice cores were used to inform our flow models of Icelandic glaciers and to figure out how they develop and flow in time. But what I was really interested about learning was how the sun develops and flows in space and time. And so I used all of that fundamental research and that training in Iceland to pull forward into my doctoral work in Norway at the Rossland Center for Solar Physics in Oslo. Um, During my career, I have also had the absolute joy of being involved in outreach programs. This was one during my doctoral work in Norway. I partnered with Hurtigruten Expeditions. Hurtigruten is a Norwegian word that just kind of means the fast route. And together with this cruise ship, I sailed a total of about 15 weeks up and down the Norwegian coast, in and out of places where we see a lot of northern light. And so I sailed as both a solar physicist, but also as an aurora expert, helping guests understand what they were experiencing in the Arctic winter. And of course, I also worked here in the United States at Badlands National Park. As their resident astrophysicist, it was my job to interpret the sky to our visitors. And that means night sky stuff, but it also means day sky stuff. And our most prominent object in the daytime sky, especially in South Dakota in the summer, is the sun. And so this strange red circle that you see is actually a picture of the sun that I took through a solar telescope that's very special. This type of filter on that solar telescope allows us to see the lower atmosphere of the sun. And I'm going to show you more observations of the lower atmosphere of the sun, but you can see kind of some cottony things sticking out of the edge of the sun. Those are traces of solar magnetic dynamics. And we're talking a lot about magnetic fields today, so buckle up. But of course, today, I have a job as the outreach lead for NASA's multi-slit solar explorer. This cartoon is what the explorer will look like once it is assembled. It is currently being designed, the instruments are being built, and the science is being perfected as we speak. We also have a brand new outreach program that was funded in December of last year. We have 3 local Bay Area, California partners, that being the Chabot Space and Science Center in Oakland, California, the California Academy of Sciences in San Francisco, California, and the Boys and Girls Club of the Peninsula, particularly the East Palo Alto clubhouses in the Bay Area in California. So together, all 3 of us and our many other partners um, curate together science outreach products and activities, visualizations that help us communicate the science concepts of MUSE. And I'll talk about MUSE in a lot more detail later. So the thing that we're most interested in studying around my circles is the sun. And this is an image of what we believe the sun to look like from its very inside to its very outsides. And to understand the sun, what we need to do is we need to go back to the basics. So let's all orient ourselves to the solar basics and get on the same page. The first thing is that the sun is a star. Now, it does not look like or feel like the stars that we see in the night sky. And that's because the sun happens to be the closest star to us. So we experience the sun and the sun's influence very differently from our experience of stars that are much farther away from us, that are not in our solar system and not affecting us in the same way as the sun. Stars, like the sun, are made of a material that we call plasma. Now, this is not astrophysical plasma. This is astrophysical plasma. This is not biological plasma that's in your blood. When I say plasma, I'm speaking about astrophysical plasma, which is just gas with a little energetic kick, a little electrical kick to it. You can think about it that way if you want to. And then, much like myself, the sun is happily sitting in its midlife. Based on its mass and amount of fuel that it can burn, we estimate that the sun is about 4.5 billion years old and has about 4.5 billion years to go, roughly. And so we're very happily sitting in a very stable time in the sun's life, which allows us to enjoy the type of lifestyle that we have here on Earth. So let's start in the very middle of the sun and go through its layers. In the middle of the sun, we have a thermonuclear fusion machine that is smashing hydrogen atoms together to get helium atoms. And that process requires really intense temperatures and really intense pressures. So the core measures in at about 10 million degrees. And these processes release a ton of energy. And that energy has to go somewhere. We know that. We know that the sun releases energy because we experience it as light and heat. But how does it actually make its way from the core to us on Earth? Well, the first layer after the core of the sun's interior is known as the radiative zone. This is where the sun is radiating plasma away from the sun's core. We would ideally like this to happen quickly and expeditiously and orderly, but instead, it doesn't. This is more akin to a solar pinball machine. There's so much going on in the radiative zone and a lot of things to run into and get in the way that it can take over 100,000 years for energy to make it from when it leaves the core to outside of the sun. So if you're from the Bay Area, that's a little bit like sitting in traffic on the 280 or the 880 going up into San Francisco. But it is not an expeditious or a quick process. But eventually, when that radiation makes it through the radiative zone, the method of heat transfer in the sun changes. And it changes in this region just below the surface that's called the convection zone. So instead of moving heat by radiation, the sun starts to move heat by convection. And that is where we have hot plasma rising and cool plasma sinking, and hot plasma rising, cool plasma sinking in these circular cells that we call convection currents. Now, something really important happens at the base of the convection zone and the top of the radiation zone. Because if you have plasma radiating sort of outward, and then you have plasma sweeping up into these big circular currents, you're going to get an interface between those two plasma flows, something that we call a plasma shear. And since plasma has an electric kick to it, that's going to change the electric field locally there. And we know from physics that if we have a changing electric field, we get a magnetic field. So this is where the sun's magnetic field is generated. It is not generated in the core of the sun. As far as we know, it's generated at this interface between the convection zone and the radiation zone. There is a name for this boundary. It's called the tachocline. And to me, that's a very funny word, and it sounds a little bit like taco line. So I'm just going to denote it with a taco so that you remember that it's important and can remember that at the taco line, or at the taco, at the tachocline line, that is where the sun's magnetic field is generated. Okay, stick a pin in that, remember it for later. So how do we know that the sun has a magnetic field at all? Well, we can see it. We can see its effects, rather. The surface of the sun is a little bit of a selfish thing. because we define the surface of the sun as the first layer that we as humans can perceive, because this layer of the sun glows in light that's very easy for our eyes to see. So we called it the photosphere or the light sphere. And on the photosphere, we see very direct evidence of the sun's magnetic field. Sometimes on the surface of the sun, we get these dark freckles on the sun's face. These are called sunspots. What are they? They are regions where the sun's magnetic field is so intense that it actually stops that convection current underneath it from happening. And if that convection current stops, the sun loses its ability to move heat efficiently. And if it loses the ability to move heat, then that plasma is going to cool down just a little bit. Now, it's still, for us, very, very hot plasma. But where that magnetic field is sticking out of the sun, you can kind of imagine in 3D a tube sticking out of that sunspot right straight towards you. If that plasma is not able to be heated efficiently by convection, then it's going to cool down a bit. And if it cools down a bit, it looks a lot darker. And so that is evidence of slightly cooler plasma because of magnetic flux. And what we get then is a sunspot. Now you can see around this real observation from the Swedish Solar Telescope that convection is happening around the sunspot. And the majority of the sun's face is that type of plasma. The majority of the sun looks like this. This is what we call quiet sun. Now, one of my colleagues at NASA, Nikki Weil, who is the mission scientist for the Punch mission, which is actually launching today, so congratulations, Punch. It's another solar mission. She likes to say that there's never a quiet day on the sun, and I like to agree with her, although in the field we call this quiet sun. Now, quiet doesn't mean that there's no magnetic field. It just means that the magnetic field that is there isn't strong enough to stop that convection current. And that's why we can continue to see convecting cells of plasma in the quiet sun. Okay, so what if we go just above the surface of the sun into the sun's atmosphere? The sun's lower atmosphere is made of, well, it's difficult for us to see without an eclipse, which is true of the sun's entire atmosphere. But the chromosphere, or color sphere, is where astronomers first discovered helium. This is why we know helium exists. And it's also been, as you can see from this image, it's been described by astronomers as sort of a burning prairie. That's sort of what it looks like, isn't it? But it is also the first time where we get a nice 3D representation of what the magnetic field looks like, especially in this image on a smaller scale. Because as it turns out, plasma loves magnetic fields. Plasma loves to stick to magnetic fields. And so we can use plasma as a tracer of lines of magnetic field, or magnetic field lines, as we call it. And so all of the little, I guess, burning prairie grasses that we can see in that image, they are tracing local magnetic fields there, especially this one here. But I can do you one better. From a larger perspective, up above the solar chromosphere, above the lower atmosphere, we have the upper atmosphere. This is called the corona, which just translates to crown, right? This is the solar crown. And we cannot see it very well without an eclipse because it doesn't glow very brightly in wavelengths that our eyes like to perceive. It glows very brightly in X-rays and extreme ultraviolet light. So this is an observation of the sun by an instrument called the Solar Dynamics Observatory. And what that does is it looks at the sun in, for example, in this image, ultraviolet light. And this particular type of ultraviolet light tells us where the sun is magnetically connected. All of the bright points of light here show us where the sun's magnetic field is making a little loop and connecting back to the surface and being rooted by those sunspots that we saw on the surface. Now, the dark spots do not tell you where there's weak magnetic field. They tell you where there's open magnetic field, where the field is not connected back to the solar surface. Instead, these are what we call open field lines. And solar plasma is able to hitch a ride on those open field lines on a solar superhighway out into space and affect us with what's called the solar wind. The solar wind fills interplanetary space, and it is helped by these darker regions here that we call coronal holes, where the lines are open and the plasma can hitch a ride. All right, so what's the problem? Why do I have a job? Why do I keep getting funding? Why are we still thinking about this? Because it seems that we have a pretty decent understanding of how the sun works, right? Well, sort of, but there are still a lot of mysteries surrounding our closest star. I told you earlier that the core of the sun is about 10 million degrees. What I did not tell you is that the surface of the sun is about 5,000 degrees. Okay, that's fine. That means that all of the heat from thermonuclear fusion has sort of radiated and convected up to be about 5,000 degrees at the surface. All right, fine. The issue is that once we go up into the chromosphere and then up into the corona, we start seeing temperatures of 1 million degrees, 2 million degrees, 6 million degrees. See, that doesn't make a lot of sense if nuclear fusion is the only heat source on the sun. So this is known as the solar coronal heating problem because it is a problem with the way the solar corona is heated, right? And it implies that there must be an extra energy source providing that extra energy, which eventually dissipates in the form of heat in the solar corona. Okay? As with most things in my life, at least me, I'll speak for myself, the secret lies with the taco. Do you remember what happens at the tachocline, where I've denoted it with a taco? That is the interface between the convection zone and the radiation zone, and that is where the sun's magnetic field is generated. As it turns out, magnetic fields hold intrinsic energy, and that energy can be converted to speed and heat. So, we believe that at least part of this problem can be solved by understanding the sources of solar magnetic energy. And we know that the sun reveals its magnetic field in many different ways. It reveals it in active regions, like these strong magnetic field sunspots and these big coronal loops. It's there in the quiet sun, even though it's maybe not quite as obvious. And a third thing that I'm not going to talk about is waves, but the sun has waves, magnetic sound waves, that propagate through the sun and move energy from A to B. So I, in particular, like to study the quiet sun. And we can do that in a couple of different ways. We can look at satellite or telescope observations of the quiet sun, or we can look at computer simulations. And the first story I'm going to tell you has to do with a computer simulation of the quiet sun. Now, during my doctoral work in Norway, we had an in-house simulation of the solar atmosphere. It was called Bifrost. It is called Bifrost. It was developed there over many decades. And what it is, it's a little cube of sun. And it starts at the very bottom here with a slab just underneath the surface of the sun. And then as we move up, we have a slab that is the surface of the sun. And above that, it's all solar atmosphere, right? For this simulation, the free parameter is the magnetic field. So we insert an initial magnetic field, and then we allow it to evolve as we believe the sun would allow its magnetic field to evolve. And if you want to understand how magnetic fields impact their surroundings or are impacted by their surroundings in a computer simulation, you can do a couple of different things. I like to think of simulating magnetic fields as sort of having a pot of spaghetti in water. If you want to know how the spaghetti interacts with the water and vice versa, you can do one of two things. You can either stick your hand in the pot and move the spaghetti in very specific ways, and then see how the environment is affected by it. Or you can turn on the boiling and see how boiling spaghetti interacts with its environment. Our simulation turns on the boiling and allows the magnetic field to self-consistently evolve, consistent with how we believe convection to work and how we believe magnetic fields to work in the sun's atmosphere. So we set up what we thought would be a relatively boring simulation, balanced magnetic field, not much going on. We just wanted a quiet sun so that we could do weird things to it later and have sort of a uniform background to play with. However, before we got to that phase of being able to insert strange things into the simulation, something weird happened self-consistently in the simulation. I saw in my atmosphere that I was getting this big slab of heat. And that was strange because we didn't put it there. We didn't put any sort of magnetic fields that should generate something like that. We didn't ask for this. So then my task was to think about all of the ways by which the simulation could have generated this huge slab of heat. Now, going back to what we know about magnetic energy, because we know that magnetic energy can be transferred to heat, we need to understand what magnetic fields do, how they behave, what they like and don't like. And one of the things that is a characteristic of magnetic fields is that there is no north magnetic field without a complementary south magnetic field. Some of you might be familiar with electric fields and electric charges, protons and electrons. Protons can exist without an electron. Electrons can exist by themselves without protons. Magnetic fields are not like that. There is no north magnetic pole without a south magnetic pole. At least we don't really observe that happening in nature, right? We also know that magnetic field lines hate to cross each other. They won't do it. So as you can see in this GIF down here, we have blue magnetic field lines approaching these red magnetic field lines, and they're dangerously close to crossing each other. So once they hit that middle point where they would have crossed over each other, they don't do that. Instead, what they do is they do something called reconnecting. This is magnetic reconnection. And they leave the area as a half blue, half red magnetic loop. Okay? Now we know from physics that if there is a dramatic change in a magnetic field, like what happens during reconnection, that generates a lot of electric current over a not so big space. Okay? And if you have this really dense bit of electric current, that can dissipate as heat. And so that's what we thought was going on in our simulation. And long story short, when I finally was able to figure out which magnetic field lines were the culprit behind this heat, this is what they looked like. The heating here is now shown in yellow. And what we saw is that we had these blue and red magnetic field lines in active reconnection with those green lines above it. This generated plasma that was 1.5 million degrees nearly, and energies that are consistent with baby solar flares that we call nanoflares. So we accidentally simulated a nanoflare self-consistently. Because typically, if you want something that looks like these red lines here, this is called a magnetic flux tube. It's a very cool name for having essentially a magnetic rope. If you want something like that traditionally in your model, you put it there. You stick it underneath the solar surface down here, and you let it rise by convection and buoyancy. You let it rise through the atmosphere and then see what it does. This is something that's called flux emergence. But this, what we simulated, was not flux emergence. We spent a lot of time tediously tracing every single one of these field lines to determine that they did not begin beneath the solar surface and rise. They began in the atmosphere, and they coalesced self-consistently in the atmosphere to form that rope. And this is sort of what that looks like. We start with this tangled mess of spaghetti. And as you'll see over time, eventually it twists together to form a magnetic field rope before it gets reconnected with those overlying lines that are not shown here. And what we were able to see after painstakingly tracing each individual field line and making sure we knew that that was the field line we needed to trace, we demonstrated processes that, to our knowledge, have not been modeled before, at least not in solar simulations. These are really old theories of magnetic field theory that we were able to demonstrate in a modern simulation that traditionally people didn't really know how to model before. And the really lovely thing is that it happens self-consistently in our model. It excited us, but of course, you know, most people don't go around thinking about magnetic fields and how you make a magnetic flux rope. So what? Why does this matter to people? Well, it is really important for us to understand what we're looking at when we're simulating something. When something surprising happens, this is how research works. We work to understand what caused that strange, unexpected thing. And even more importantly is what we can do with this information. This informs what we knew or know about how nanoflares might form, about how magnetic fields might work on the sun. And so, can we observe something like this? Do we have instruments that could observe something like this? That was our next question. So back to our flowchart of solving the problem of solar magnetic energy and coronal heating, I mentioned we can look at satellite observations. So I'm going to bring us back to what satellite observations might help, how satellite observations might help us with this. A cool thing that modelers can do is make something that's called a synthetic observation. Now, a synthetic observation helps us understand what a telescope might see if it were observing the thing that we just simulated. In my case, an accidental nanoflare. So I took a slice through my nanoflare from the top down and from the side. And you can see this kind of X-shaped reconnection that's happening there. This is the nanoflare if I were to image it in ultraviolet light, a similar type of light to what the MUSE mission would be able to see. So to make a synthetic observation, I take my simulation and then I figure out how sensitive the MUSE mission should be to that type of light that I'm imaging it in. And then what's the resolution roughly of the MUSE mission expected to be? And what we see is that MUSE is pretty good at being able to look at, or at least our synthetics, MUSE should be really good at being able to find some really important bright points in our accidental nanoflare. And even better, this last column here is an instrument we already have in space, whose resolution isn't quite as good as MUSE's resolution is going to be. And if we saw something like this on the right-hand side, it would be really difficult to interpret what that is, right? You'd have to be really creative and not so certain about your interpretation of this observation. MUSE is a lot more clear. And if we have a bunch of simulations that do things like this, then it can inform our observations as well. So not only does our good data from satellites inform our simulations so that we have better code, our simulations are playgrounds for things that we have yet to observe very well. And they inform each other. It's a very symbiotic relationship. Okay, so this great instrument MUSE, what is it? What's it going to do? Well, this is a cartoon of MUSE in orbit. MUSE is what's known as a medium-sized explorer, a mid-X, and it will be scheduled to launch in July of 2027. MUSE is a combination camera and light collector. Cameras are light collectors, but it has a different light collector called a spectrograph. MUSE will not be orbiting the sun like European Solar Orbiter or Parker. Instead, it will orbit the Earth in low Earth orbit, polar orbit. We use polar orbit for solar missions because we don't ever want them to go behind the Earth. We don't want them to experience nighttime because then you lose half of your observation time, right? Whereas the sun and the Earth's shadow, we can't see it. So we put these solar missions in polar orbit So they're always staring at the sun. They're always right at the daytime side of our planet. Now, MUSE is built by legacy technology from its big sister, which is called IRIS. This is an observation from IRIS. IRIS is already in space. IRIS continues to be in space. And IRIS is also in low Earth polar orbit. IRIS is also a combination camera and light collector, but the type of light collector that's on board IRIS is what's called a single slit spectrograph. Now, what a spectrograph does is it forces light through a tiny little slit, and doing that disperses the light into what's called a spectrum. Now, from the spectrum of the light, we're able to infer physical processes about the plasma that we're observing along that slit. We can determine temperature. We can determine relative speed of the plasma, and we can determine turbulence of the plasma, which gives us information about what the magnetic field dynamics might be there. Okay. Now, this is a real observation from IRIS, and you can see that it is observing many small scale events on the sun, but also these huge, massive events in the sun's atmosphere. Right in the middle, you might see a tiny little horizontal black line. That is IRIS's slit. That is the spectrograph aboard IRIS. And we can get a lot of information from that spectrograph, but as you can see, as it's nervously darting around, it can't capture the whole of that giant explosion. That giant explosion is driven by magnetic events on the sun, but IRIS can't get spectral information from the whole thing because it's simply too hard with one slit to capture that whole event, even if you get it in the camera. This is essentially what a single slit spectrograph is doing. If you force light through this one little slit, you're going to get one slit worth of spectra for each pixel along that slit. And from those spectra, for example, we can flip them into maybe an image of temperatures along that slit. But that line of temperatures doesn't tell us a whole lot about the big picture of what's going on. It can help us understand what types of spectra give what types of temperatures or other physical properties, but it doesn't give us a big picture. This is where MUSE comes in. MUSE is called the multi-slit solar explorer, which might give you an idea of what MUSE is going to do. MUSE will have not one slit, not two slits, but 35 slits in its spectrograph. And by doing that, by forcing light through 35 slits, we can get a much bigger image, not only of dynamic events happening on the sun image-wise, but dynamic events happening on the sun spectrally. We will have several lines of spectra, which then we can invert into a much better picture of temperatures, for example. And we can get a much better image spectrally of what's going on. And in fact, the synthetic observables for MUSE look so good. On the left-hand side, this is a simulation of a much bigger flare than the one that I simulated in my work. On the top row, we have temperatures and intensities. And on the bottom row, we have Doppler shift or relative speed. You can see on the left-hand side, this is a simulation of the flare. And in the next column to the right, we have the synthetic observables of what MUSE should be able to see during that dynamic event. Do you see how well MUSE is able to kind of freeze that plasma in space and time and get a really good idea of how that flare is developing versus the four boxes on the right, where even our best single slit can't deal with something as dynamic as this flare. What you get is a really smeared out version of what that flare is and was, but you don't get an evolution of what that flare is and was. Does that make sense? So we're really excited about the new technological and spectral advances that MUSE will offer us. And why do we need MUSE besides just getting better spectra? Well, better spectra of the sun helps us understand the conditions on the sun that not only heat the atmosphere, but point to the magnetic dynamics of the sun. I'll be honest with you, we're really bad at predicting solar flares. We can't do it. We can see sort of where the active regions are, and we can see that there should be something maybe flaring at some point in the future, but we have yet to really nail down the trigger mechanisms of a solar flare. MUSE, looking at the sun in such fine detail, both in space-time and spectrally, will inform our understanding of these dynamic events much better. And it will also inform our understanding of what launches the solar wind. As MUSE is built from legacy technology, MUSE itself will eventually be legacy technology that will develop better instruments in the future and provide better constraints on our computer models so that we have these playgrounds that we can work with that are a better analogy to the sun than what they are now. I think it was George Box who said all models are wrong, some of them are useful. Our goal is to have the most useful models that we can have to understand our star much better. And I spoke about solar wind a little bit. When we have the constant onslaught of solar wind, sometimes with bigger magnetic explosions on the sun, we get extra plasma shock waves in the solar wind, and that impacts us here on Earth. We are shielded from the brunt of those shock waves by our own magnetic field, our own planet's magnetic field, but that doesn't mean that we're not impacted by it. This is detrimental to our communication satellites. It scrambles our GPS positioning. It makes it really hard to communicate via radio over large distances. It can even induce currents in our ground that can mess with our electrical grid. And these are things that make our infrastructure vulnerable or weak. And so we need a better way of understanding when those things are coming towards us and how they impact us. And then, of course, when we have human spaceflight, we have astronauts on the International Space Station and soon the moon. They can't be outside during these events because the energetic particles are harmful to them. So we need a better understanding of these things. This is a little NASA video of how we're impacted by these shock waves and how our Earth magnetic field, how our geomagnetic field spares us from the brunt of that radiation, but we still experience it because that shock wave is strong enough to push our own magnetic field together until it itself reconnects. And we have reconnection on the night side of our planet, which accelerates particles down to the poles of our atmosphere. Not only does this create harmful things, this creates beautiful things. These are the northern lights as seen through my phone last month in Alaska. We had these wonderful, wonderful deep greens and pinks in these auroral substorms that are a direct result of solar magnetism. And we don't just get these in the northern hemisphere. We get these in the southern hemisphere too. This picture was taken by James Garlick. I swiped it from his socials, but all credit where credit is due to James Garlick. This was a picture that he took from Tasmania last year in May. And so we have these very beautiful things to look forward to and study as well. And we're so excited about what MUSE is going to do to inform ourselves and inform our study, inform our understanding of our closest star, what it can do, what it's capable of, and how we can move forward in the future with our relationship with the sun. I'm so honored to be able to learn together with you and talk to you today. Thank you so much for having me. And I think I'm just going to have this video of real observations from the Solar Dynamics Observatory just playing in the background while I address any of your questions. So thank you. I'm happy to take questions.
Thank you so much, Rebecca. That was really fantastic. I learned a lot more about the sun. I'm still thinking about the spaghetti analogy and sticking my hand into it's a very nice texture experience that I'm thinking about. So while we're waiting for some questions to come in, and I'm sure people online will have tons of them, I wanted to ask you about your outreach experiences because they sound really fascinating. So you mentioned that you were a solar and aurora scientist for a cruise ship. And I was wondering if you could maybe give us a little bit more context for what that means and what it looked like for you.
Absolutely. So I sailed with Hootadoot expeditions, and these are expedition ships that have science centers on board their ships. So they have lecture halls, they have microscopes, they have active citizen science projects and active citizen science collaborations going on. So I joined as one of those. we collaborated with a citizen science project called Aurorasaurus. And basically, what that is an initiative to get ground-based aurora observations, ideally as they're happening, so that we can understand how good or bad our space weather predictions are in real time. And this was an ideal thing because we were sailing up above the Arctic Circle along the Norwegian coast. And for those of you who are familiar with Norwegian geometry, at some point in the country, we cross the Arctic Circle and we go up kind of around into the high Arctic. And we're right under what's called the auroral oval, which are latitudes where we're very likely to see northern lights. And so for me, what that involves, what was basically giving some brief lectures like this one about the origin of northern lights and that they're very solar in origin. And then the prediction of space weather events like northern lights. How do we predict these things and how good or bad are we at it? And then also how we can contribute to citizen science by making our own observations. And so it was a very fun, kind of as tangible as space can be, I suppose, where we would learn a little bit about the theory and then we'd go outside on deck. And sometimes almost every night we would get northern lights above our ship. And so whether we were on the ship or on shore, we experienced these really dazzling storms, and not one of them is the same. So we're able to kind of see and understand the different forms that auroras can take, the different colors that auroras can take, why it's harder to see with our eyes than our cameras in the dark, and sort of calibrate expectations and understandings of how it is to chase auroras in the Arctic and I suppose the Antarctic, but I've never been down there.
That would be amazing, but I get too cold too quickly, so I don't think I could survive the Arctic or Antarctic. So that's really interesting. You were also talking to me earlier about, what is it, Stan? Am I remembering this correctly? It has a very person name that's an aurora related
Steve.
phenomenon.
Oh,
Steve.
Steve. Yes. I was like, Stan the Eminem song. Eminem is from Michigan, so we're homies. But I mean, not personally, but I mean spiritually. So Steve is a fantastic example of citizen science working the way that it is intended to work. So Steve auroras they don't form quite as polar, quite as high latitude as I suppose regular auroras. They form at like high mid latitudes. And what Steve auroras are this kind of wispy ribbon of purple gas and then a picket fence form of green auroras. And what that picket fence probably is currents that align with Earth's magnetic fields and are forced and informed by what's called kinetic waves in the atmosphere. And the reason that it's called Steve is because citizen scientists named it. Citizen scientists, particularly in Alberta, Canada, were some of the first modern skywatchers to capture really prolific and wonderful photographs of the Steve phenomenon. And upon bringing that to the scientific community through the Aurorasaurus community, we now have an active and engaging academic research program surrounding what Steve auroras actually are. What are the similarities and differences in kinetics, in chemistry between Steve auroras and regular auroras, for example? Why do Steve sometimes form and sometimes not? These are still open science questions that are being actively engaged. And it was the citizen scientists that brought this to the attention of scientists because while while the science community had all of these detectors around Canada, they didn't quite recognize that they were capturing Steve signals in the data because they weren't looking for it. So this is an example of where citizen science is science. Science is truly for everybody, and we can make really wonderful discoveries just by looking up. The name Steve was named by a guy named Chris in Canada. He was referring to a movie called Over the Hedge, a cartoon film, where the animals in the film, they encounter this big hedge and they're frightened of it because they don't know what it is. And we weren't necessarily frightened of Steve, but we didn't know what it was. And so in the film, the animals call the hedge Steve because that made it less threatening. And then they knew what it was. It's just Steve. And so this is according to Chris's self-description. And so he thought, let's just apply the same logic here. We don't know what it is. So let's just call it Steve, because then we know what it is. And of course, once the science community got their hands on this, Steve now stands for strong thermal emission velocity enhancement, because that's what we do with with acronyms. But I mean, it kind of works. Like in this case, Steve auroras are a strong thermal emission. It's really, really hot plasma up there in the Steve aurora atmosphere in the ionosphere. And it is a velocity enhancement. Steves are driven by what's called a kinetic wave, and that's a velocity enhancement in the atmosphere. So in this case, something kind of very almost lovely and silly as naming something Steve turned into something that is actually very physically correct. So the story of Steve auroras from first modern detection to active scientific projects now is such a gorgeous, lovely story of citizen science working as intended and how it should work. Science really is for everybody. It just takes a curious and driven mind.
That's amazing. Thank you. I will add as a caveat to that, a curious and driven mind and access to all of these amazing resources that we need to do the science. And unfortunately, not
Right.
everybody has access to that.
That's right.
But we have a question from the chat. Anthony Gomez asks, can you say something about the solar cycle and flipping the poles?
Yes, Anthony, thank you for bringing that up because I didn't talk about it in this talk. So the sun is not always magnetically the same. The sun goes through a magnetic cycle that is about 11 years long, where the global magnetic field of the sun, so when I say global, I don't necessarily mean the Earth, I just mean the overall geometry of the big scale magnetic field on the sun. The global magnetic field goes from being kind of like if there were a bar magnet inside the sun. If any of you have ever played with a magnet and dusted it with little iron shavings, the iron shavings trace the shape of the magnetic field, and it kind of is apple shaped. It just kind of looks like it's coming out of the top and into the bottom like that. That's called a dipole. The global magnetic field goes from being a dipole shape to kind of a torus shape. And when it's that torus shape, there's a lot more small scale magnetic loops and smaller scale activities that are happening closer to the equator of the sun. And this happens because the sun is not rotating, first of all, like a solid body. It does rotate, but not like a solid body. It rotates like a plasma body because that's what it is. As a result of these rotational forces, the magnetic field along the equator is dragged around the sun at a different rate than it is dragged around the poles. It's faster around the equator than it is at the poles. On top of that, we have convection cells working in the solar interior. And on top of that, we have bigger plasma currents happening in the surface and interior of the sun that are all working together to move this magnetic field around more or less all of the time. So we start with a pretty apple-shaped dipole field. And because of these flows, we kind of move over to a more toroidal torus-shaped field with smaller scale currents. That's where we see the maximum activity. And then eventually, these things migrate to the poles, annihilate each other, and move back up to the pole, but in the different direction. So then the magnetic north has become the magnetic south. And that happens approximately every 11 years at any point in the cycle. So we are currently in solar maximum. Solar maximum means that we are sort of in the nittiest gritty of that toroidal field and all of that, those small scale loops and lots of magnetic reconnections happening. But the last one was in 2014. So we're about on schedule, 2025. That's an 11-year break. It's not necessarily a black and white cutoff 11 years every time exactly. This is just something that we've observed in the cyclical behavior of the sun. And the way we actually tell when we're in a new solar cycle is by looking at the sunspots. So sunspots, we get more of them when the sun is more active, when the sun's kind of equatorial fields and mid-latitude fields are more stronger, and then we get bigger sunspot groups. Sunspots tend to travel in groups. And in one hemisphere, northern or southern, they will have a leading spot with a leading polarity, which tells you a little bit about the polarity of its pole. In the other hemisphere, let's say the southern hemisphere, the leading spot will have the opposite polarity. So the way we know that we've entered another sun cycle is if we have two sunspot groups in the same hemisphere with different leading polarities. That's sort of when the community starts to make that judgment call, because we're somewhere in the transition between having this active toroidal field and once again having a very orderly, quiet poloidal field, dipole field, but with an opposite polarity. Okay. So going through that cycle is one thing on the sun, but we're affected by it on Earth. When we have these orderly poloidal dipole fields, we don't experience as many magnetic reconnection events that result in big shock waves and space weather. And so we experience a slight dip in problems with communication based on the sun, or even northern lights. There still can be northern lights, but you have to be at the right latitude to see them, and they're generally not quite as strong. Those of you who live in polar latitudes can possibly attest to this, that you still sometimes see northern lights when we're in solar minimum, but that we're much more likely to see stronger storms and more frequent storms when we're in solar maximum, when the sun is flinging things at us left, right, and center, when it's in that more toroidal field phase. Okay. So that's why we experience kind of a periodicity in how we experience northern light storms. The ones that happen during solar minimum are not likely to reach as far south as perhaps the middle United States or southern Europe in the northern hemisphere. But the ones that happen in solar maximum can go quite far south or north, depending on which hemisphere you live in. The most recent, I suppose, in recorded history, super geomagnetic storm that happened was in 1859. This is regarded as the Carrington event based on the solar physicist who recorded and observed that event. In 1859, luckily, the prevailing form of technology was telegraphs. And so the world didn't experience a total energy grid knockout that it may very well have experienced if this happened today. But what they did see was telegraphs sending by themselves without being connected to any sort of power source. Because remember, these currents are coming down in the atmosphere, but they induce currents in the ground. And so you get ground currents that you otherwise would not have had. And many telegraph operators were reporting to doctors and hospitals with burns because there was so much energy in the air. Now, this would be much more catastrophic today, but the cool thing about that storm is that it sent northern lights as far south as Colombia, South America, and as far north as Kansas, Australia. So northern Australia and northern South America. It was basically only the equatorial latitudes that didn't see any sort of aurora activity during that event. Now, of course, catastrophic today, but very, very cool to think about the possibility of being hit just right or wrong. That possibility always exists, and it scales very well with the sun's magnetic cycle. So I hope that answered your question.
That's super cool. I don't think anybody could see my face, but I think my mind was just sufficiently blown by that. So we have a couple more questions for you if you have the time.
I do.
One of them is, could you talk about maybe using AI or machine learning in the research that you do?
Absolutely. So one of the things that AI is really helpful for is lowering the very blessed burden of our data. We have a lot of data coming down from many different satellites and many different computer codes as well. Now, what we tend to do first is build code that doesn't rely heavily on AI. And then once we have that code down, we use AI to beat that code. Because what we want is speed and efficiency. And we're not burdened by the limitations of human labor, working hours, human mistakes, things like this anymore. We can use AI to do sort of tedious first sweeps of the data that we used to rely on people to do. I guess when I was an undergrad student. That would sort of be my job, is to do a tedious first sweep of the data to see, okay, this is noise. This has a specific signal that we don't need. We're not looking for it. We can now use AI to do that. Many groups are using physics-informed machine learning to detect sunspot cycles, features on the sun's surface, magnetic features, things like this. With the MUSE mission, our biggest challenge at the moment is what's called spectral disambiguation. So if we have this huge raster of spectra, inevitably, some of them are going to overlap one another in ways that are not necessarily obvious to disentangle, right? We have to deal with that in a way that's physically reasonable, but computationally accessible, right? So the challenge that the scientists are solving currently in the Muse Science Group is how do we do this most expeditiously? And while the immediate conclusion is not to use AI, the future conclusion is to potentially use an AI code to beat our current disambiguation codes. Because we don't have real data to deal with yet from Muse, we need to test codes that we know exactly what's going on. And we don't have enough training data to train up an AI code to do what we need to do to disambiguate those spectra yet. But what they're doing is there are many ways that are also machine learning informed that you can use to disambiguate these spectra. The problem is they take a really long time. And if we run those particular codes, it's too computationally expensive. The data products are not going to be available as much as they're coming in. We're going to end up with a backlog. That's not what we want. So eventually in the future, we have some AI professionals working with us and on the Muse Science team to figure out how to beat our own codes, especially once we have an adequate amount of data coming down from the machine. So we're very AI friendly and we use it for a lot of things. It's just that we have to be really careful how we're informing the AI, how we're training the AI, and that we're doing all of that appropriately.
That's super cool. And I want to apologize. India Jackson asked that question, so
Thank
thank
you,
you.
India.
So we have another one. Natasha Ristic asks, can you make any predictions or forecasts, or have you heard any maybe, about the likelihood of another major storm this year, like the one in 2024 in May?
Well, so unfortunately, no. Thank you for this question. This is really good. The space weather physicists that are among my heliophysics colleagues are getting a lot better at their modeling. The problem is, again, speed. So while it is really difficult and impossible to predict what the sun is going to come up with once it rotates toward us, there are a couple of clues we can look for. First of all, is there a big dark spot on our ultraviolet image of the sun? Remember, dark spots are not spots where the field is zero, it's the spots where the field is open. And so if you have any big explosion that comes next to that open field, that plasma will essentially get on the bullet train right towards the Earth and create a plasma shock that eventually will hit us. And so that type of stuff is what we're looking for. However, that's still not a guarantee. The last thing that shock wave needs to do is reconnect with our magnetic field. Now, Earth currently has a northward facing magnetic field. So I don't know if you've ever taken two magnets of the same polarity and tried to stick them together. They don't attract each other. Opposites attract in terms of magnetic fields, right? So if we have two northward facing magnetic plasma entities, like our magnetic field and that plasma shockwave from the sun, that reconnection is not going to be efficient. Maybe something still happens because the kinetics are intense, but we may not get a geomagnetic storm on par with May or October 2024. Now, the best geomagnetic storms, the most efficient ones, happen when you have a strong, fast, dense, southward facing shockwave from the sun. Because then when it comes and hits Earth, reconnection is really efficient. And then we get those really intense auroral substorms, sometimes for days on end. And we get an atmosphere that just rings with the effects of that for months, if not years. We have radiation belts around the Earth that are a result of those storms today that we didn't have before those storms. And so that kind of thing stays around us for a really, really long time. The prediction is the hard part. We can sort of know what's going on in the sun, but we have no idea what it's going to do by the time it hits the Earth. We have satellites in space that measure the density and the speed of the plasma as it comes in. So we get an idea of whether it's a fast solar wind or a slow solar wind or what. But we really don't know how to calculate that very last magnetic direction before it hits the magnetic field of the Earth, because it can change a bunch of times on the way, and it does all the time. Parker Solar Probe, as it flew through the solar wind, measured all these switchbacks in the plasma that we didn't know existed. And so we really don't know so much about what happens between the sun and the Earth. I can say we're getting better, but I can't tell you whether or not we're going to have another May or October 2024 storm. I hope so. My fingers are crossed right along you.
Yeah, I would certainly love to see that. And hopefully maybe the aurora will get down to Tokyo. That would be nice for me.
That would
Um,
be so
so we're running out of time, but I think it would be really cool for you to tell us a little bit about your path that got you to where you are right now, and how maybe some people could follow in your footsteps in the future.
Sure. I have a really non-linear path that started as a linear path. I think a lot of times we are given sort of a blueprint for how these types of jobs work. And I'm not saying to, throw out all your plans and throw out all your blueprints, because they can be really nice structures that you can lean against when you're feeling a little bit directionless. But for me, the stable thing in my life that's brought me this far is a love of things like this. On days where I just felt like crud and I didn't really want to get out of bed, the idea of doing something like this was enough for me to get up and keep grinding. So, contrary to that, we have our grinding days and we have our rest days. So, learning how to do a balance between those 2 days is really important. But path-wise, I told you that I did my degrees at Michigan State, and you might have noticed that it was a really long time between my bachelor's degrees and my master's degrees. Not really long, but 5 years. And most people don't do a 5-year master's, and I certainly didn't do a 5-year master's. I did a 2-year master's. So what happened to those other years? Well, I tried a couple of things in between, and those couple of things didn't work out. Sometimes life happens. I ended up really ill. I ended up not able to work very well. I ended up needing to take a break from the field for a few years. And I think a lot of people are afraid to do that. And with me, it was a necessity for me to recover from the type of illness that I had. Sometimes that happens. But my drive for doing work like this and my passion and the idea that I could someday in the future do work like this is what kept me going through, is what kept me applying to programs and trying to figure out where I would fit in. Doing a geophysics master is a little bit weird for a solar physicist. And it took me an extended amount of time to argue that geophysics master's was worth something in the world of solar physics. You kind of have to try and fail and try again and step this way and step that way and figure out what kind of scrappy little path works for your particular skill set. And it is true of me that learning to leverage my skill set, my individual skill set that's unique to me, leveraging that into a better situation for my life is what got me here today. And if you learn how to do that, maybe a little bit quicker than I did, it's trial and error, and sometimes it takes time. But if you learn how to do that a bit quicker than I did, you might be able to find yourself in these really unique positions. Because when I found myself in Norway, I found myself with the requirement to do an outreach project, but they didn't have anything for me. So then I knew I had the skill set of communication. I knew I had a skill set of a basic understanding of how Northern Lights work. And I knew a lot about the sun. And so I reached out to the cruise ship company and said, hey, do you want a solar physicist? I'm free because the institute is paying me. Just give me a cabin and feed me. And they said, yes. So the worst they can say is no. And then you go and ask somebody else for this to fulfill this requirement or fulfill this desire or drive that you have. Reach out to people, leverage your skill set, be aware and confident in your skill set. And because I got a lot of practice speaking to people about the sun, about northern lights, that informed how I speak about my science, not only to other scientists, but also to the general public. And because of the way I communicate my science, I was at a conference that ultimately led me to the job I have today. People that were in the audience of that particular conference are people that are in charge of the MUSE mission, and they needed an outreach director. And so then they knew exactly who to look for because that job exactly matches my skill set. And so the more you leverage your skill sets, the more people will notice that you can leverage your skill set. And the more that they will know that you are a valuable and insightful person to have around. And so while my very kind of scrappy, weird path took a couple of turns that were hard and traumatic in life, how do you learn from them? How do you get back up? How do you leverage what you do have, even if it's just a little bit, into a better situation for yourself? It is true of me that it worked, and I hope that it's true of you that it works as well.
Thank you for that. We do have another question, if it's all right.
Yeah.
Their handle is She Explores the Cosmos, which is really exciting.
Cool.
And I think that they are a high school teacher because they ask, as a high school astronomy teacher, what resources are available for students to explore solar physics during this exciting time?
That's a great question. So, one of the resources that I use pretty heavily is US based. So, I don't know where you're based, but this is still accessible to you for now. It's from a division of NASA called NASA, not a division, but a project of NASA's called NASA HEAT, which is the Heliophysics Education Activation Team. And so if you were to search for NASA HEAT heliophysics big ideas, what they've done is they've come up with a repository of big heliophysics ideas, big heliophysics questions that have activities and ways to communicate this information at 3 different levels of understanding. So we have basic understandings, broad understandings, intermediate understandings, and advanced understandings of these big idea concepts. And they've spent a lot of time going through and generating that type of information. We also have heliophysics activities that go along with that. So I would check out NASA HEAT and their heliophysics big ideas repository. That should give you some good ideas.
That's great. And I actually just put that in the chat. So for those of you who are watching live, you can find that there. And we'll put it in the description as well for those who are interested in learning more. And maybe we could offline try to find some more resources to put in the description of our YouTube video so that more people can find more resources.
Excellent.
So I think we're going to end there. And I would like to thank Dr. Rebecca Robinson very much. And I just want to say that the reason why we're doing this, the reason why we have our Women in Astronomy, the Women in Solar Physics, is because women are such an important part of the scientific process, and they've been excluded, as many minoritized groups have been excluded from science historically. And we all know that having really diverse teams makes our research more efficient, makes us have better ideas, more really different ways of looking at things that help us with our research, help us to learn from each other, and really help us grow. So celebrating these women in physics and astronomy and every day is just such an important thing to do. And we hope that you continue to do that in your own practice, in your own learning. And we will continue to do that throughout the year. So again, thank you very much, Dr. Rebecca Robinson. It has been lovely hearing from you. And everyone, thank you so much for being so patient with us. And we hope to see you next time.
Thank you.